Go.
Mhm.
So
Yeah,
is there
the
any
screen
risk that,
share looks fine.
yeah, okay. You can see the cursor also?
I can see it.
Okay, good.
Um, awesome. So probably let's just wait for like a couple of minutes. Probably like some people are still trying to join the session. So um,
Sounds good. How many
mm.
minutes? Just I may get myself some water.
Oh yeah, that should be fine. Yeah, yeah. Please do.
Yeah. Okay, like 3 minutes or so. Is that okay? Or
Yeah, yeah.
okay, I'll be right back. Okay. All
All
right.
right. Cool. So yeah. So I'm just gonna begin the introduction now. Yeah, so today for the quantum error correction seminar, we have Philip who's going to be talking about the link between quantum error correction and quantum reference frame. So yeah, Philip, please take it away.
Yeah. So first of all, thanks very much for this invitation. So it would be nice also to come to Singapore one day and visit your group. So yeah, so this talk will be basically about linking two different fields, quantum error correction on the one side and gauge theories on the other. There have been sometimes already some folklore, some kind of heuristic claims that there's a link between the two. And what I want to try to convince you of that there's indeed a very precise dictionary between the two, and kind of the mediator is played by what are called quantum reference frames. And so I will try to explain this, also what quantum reference frames are. This is maybe something that that you are not familiar with if you work in quantum error correction. So, but you can think of them basically as a universal tool for dealing with symmetries in quantum systems. And so this talk is based on a paper here with my collaborator Sylvain Carozat from Dijon, and then Aidan Chapman Davies and Fabio Mele, who used to be postdocs in my group. Okay, yeah, so if you want to basically summarize in one word the content of this talk, then it's really about redundancy. So redundancy is really the hallmark, I guess, of quantum error correction, of both quantum error correction and gauge theories, and including gravity. And essentially, I guess in quantum error correction, if you don't have any redundancy, you can't really do any error correction. If you have somehow some quantum register and you encode your information without any redundancy, then essentially any unwanted interaction with the environment or so will corrupt your data in ways that you can't really distinguish from logical operations, and you wouldn't be able to do any kind of error correction. And so it is clear that somehow you need redundancy for error correction. When you have redundancy, then somehow intuitively, the hope is, of course, that unwanted interactions may really only affect redundant data without fundamentally corrupting the logical data that you have encoded. Now, in gauge theories, it's also clear that by definition, essentially, in the presence of gauge symmetries, you have redundancy. So without redundancy, you cannot have any gauge symmetry. And then on the error correction side, really the encoded logical information should in some sense also be independent of the precise states of the redundant degrees of freedom. Similarly to how in gauge theories, the physical information, so really the gauge invariant information, is supposed to be invariant of the whatever state redundant degrees of freedom you would, in whatever state they would be. And then further in quantum error correction, if you have sort of group-based codes, such as stabilizer codes, then the encoded logical data is supposed to commute with a stabilizer group, just like physical information in gauge theories has to commute with a gauge group. And so furthermore, so we have redundancy in both scenarios. And then also which degrees of freedom we would consider as being redundant in either is really a choice. And that's somewhat related to in error correction that a given code can correct many different error sets, and which error set may be interesting depends a bit on what sort of practical implementation of a code might be of interest. And in gauge theory and gravity, what kind of gauges are interesting depends on the preferences really of the practitioner. But really, so we see there's some kind of qualitative analogy between encoded logical data and gauge in quantum error correction and gauge invariant data on the gauge theory side. And basically, the aim of this talk is to try and convince you that this analogy is really, or that it's more than just a qualitative analogy, and that's really a precise correspondence. And so we want to turn this analogy into an exact dictionary. And one can ask, yeah, what might we learn from this? So for the moment, these are really foundational motivations where we want to learn something about the foundations of maybe quantum error correction and gauge theories, so that we add sort of new perspectives on either of these fields. For the moment in this talk, I will not consider really any kinds of applications of these observations, so that you might want to have in a practical implementation of a code or something like this. Those are questions that one would have to investigate afterwards. So kind of the question that arises is whether we can generally think of codes as gauge theories, or conversely of gauge theories as some kind of codes. And in order to make this correspondence work, we have to clarify a few notions that we're used to on either sides and on the other side. So for example, of course, in quantum error correction, something crucial are errors. I mean, that's really what it's about. And we also have encodings and logical data, but those are kind of concepts we don't usually think of on the gauge theory sides. We don't really normally think of maps that take us out of the space of gauge invariant data. And encodings are also not really what are standardly considered. So we have to make sense of what these kinds of concepts are on the gauge theory side in order to build a dictionary. And the key ingredient to do this are these quantum reference frames. So as I said already there, you can think of them for the moment really as universal tools for dealing with symmetries in quantum systems. And in particular, the type of framework for quantum reference frames I'm going to introduce is one that is specifically geared to gauge symmetries. And that framework is therefore crucial for this correspondence. And in this framework that I'm going to describe, a choice of quantum reference frame you can really think of as a choice of split between the redundant data in your gauge system And that redundant data will be, the redundant degrees of freedom will be your quantum reference frame, and split between the redundant data and the physical data, which is basically the rest. And in general, there will exist many such splits, which is related to there being many choices of quantum reference frame. So there's not a, the system doesn't tell you which degrees of freedom are supposed to be redundant. As I mentioned previously, it's really a choice. Okay, so then here the last bullet point is something that maybe if you're familiar with gauge theories and gravity, if not, then maybe this doesn't tell you very much, but you can think of the quantum reference frames as those degrees of freedom that when you do a gauge fixing, that you will fix. So basically the degrees of freedom, the redundant ones that you freeze out in a gauge fixing, or that equivalently that you would use to dress other degrees of freedom that are not invariant already into composite operators that are gauge invariant. So, and then what we want to build, and the first part is really a precise dictionary between quantum error correcting codes and quantum reference frames. So really at a structural level that we have, that we have a precise correspondence between the encoding operations, the different Hilbert spaces and maps between them, so that we want to flesh out in the first part. And we want to then also, at least I hope I will get to that, see what we can learn from this correspondence. If there's something new that we can learn about in this talk, it will be mostly about quantum error correction. And I should just briefly mention, so there's been previous work on codes and quantum reference frames, but in a slightly different context. It used also a different approach to quantum reference frames than the one I'm going to describe. And it was mostly in those works, quantum reference frames were mostly used as kind of auxiliary systems to deal with continuous symmetries. And they were not quantum reference frames really in the computational part of the code. Whereas what we're going to do is basically, in our case, quantum reference frames are really going to be part of the code itself. So, so it's really qualitatively different what we're going to be doing here. And so in this correspondence that I'm about to describe is really only feasible with this approach that I'm going to describe. Okay, so here's the outline of the talk. So in the first part, I will have to tell you really a little bit about these structures, the dictionary. So that will take a little bit of time. And especially if you're also not familiar with quantum reference frames, I have to introduce a bit of structure. And then I will try and see what we can use this for. So one thing in the later part of the talk, I will exclusively focus on stabilizer codes, Pauli stabilizer codes, I should say, and then see how we can extract quantum reference frames from it. And then hopefully in this part here, I will tell you how you can actually, how there's a precise correspondence between correctable error sets and quantum reference frames. And then there's a topic on error duality, but I'm not sure that time will be sufficient to get there. In fact, how long is the seminar?
Approximately 1 hour, like okay. So. Yep.
Okay. Yeah. So we see how far.
Can I ask a question?
Sure. Yeah.
So what exactly, like, what is the mathematical definition of quantum reference frame?
Yeah. So I'll come to that. So, I mean, here for the moment, it was just really a qualitative warm-up, but I'm going to tell you what quantum reference frames are in the coming slides. Okay. So, so when I summarize the dictionary, I will introduce the structure, including the basic structure that set up a quantum reference frame. Okay, but before we talk about quantum reference frames, let's first not think about quantum reference frames, but about the general structural analogy between quantum error correction and gauge theories. And so, so there's either side has a bunch of Hilbert spaces involved and maps between them. So basically, let's see how far we can go with the analogy between the two without quantum reference frames at first. And then we're going to use quantum reference frames to fill in the missing pieces, basically. So there are different types of Hilbert spaces on either side. So on the we of course have the physical space in quantum error correction that's really encoding all the possible states of your physical register. So including the redundancy really, and the redundant degrees of freedom, I mean. And on the gauge theory side, the analog of that is what is usually called the kinematical Hilbert space. That's the Hilbert space that carries all the gauge invariant and non-invariant degrees of freedom, and it carries also some unitary representation of whatever your gauge group is, just like the physical space carries a unitary representation of the stabilizer group if it is a group-based coast. Then obviously we have the code space in error correction, which is the subspace in the physical space that you need to incarnate really the code, where you want to include or embed your logical data in it. The analog of that in the gauge theory side is the Hilbert space of gauge invariant states. So those states that satisfy this relation here, so that are really invariant under the gauge transformations. So for the moment, usually it is called H-phys or H-physical in gauge theories. I'm not going to call it this way so that we don't confuse it with this one here. I'm just going to call it HPN, and why I call it PN will hopefully become clearer later on. It will stand for perspective neutral, something to do with quantum reference frames, but really for the moment, you should just think of it as a gauge invariant Hilbert space. So for the moment, I'm just going to tell you the ingredients of the Hilbert spaces here, and then we're going to talk about the maps. And And then, okay, we also have sometimes in the literature, it's considered separately, these logical spaces, which you can think of, I guess, as the abstract code without the redundancy that you want to implement, that you want to basically encode in your physical register. And here now the question is on the gauge theory side, what would be the analog of that? And this is something that one usually doesn't think about on the gauge theory side. So one of the questions is, what is that actually? And then there's also, of course, these error spaces in the quantum error correction side, where basically the target spaces to which the errors take you from when they act on the code, some other subspaces of the physical space. And there is an analog on the gauge theory side. And suppose we have an abelian gauge theory, then you can think of these other, you can think about basically the gauge invariant Hilbert space is really the trivial charge sector, or the trivial representation of your gauge group. And there will exist other spaces in your total Hilbert space that correspond to non-trivial representations of your gauge group. And you can think of those as being labeled by the electric charge. So, so indeed, in like Maxwell's theory, you could think of the non-trivially charged spaces as of the non-trivial representations as being electrically charged. And they're going to be non-gauge invariant unless you include extra degrees of freedom to compensate for how much you violate for instance, the Gauss law. So you would have to, for instance, if you're just in pure Maxwell theory without any matter, and you go to a subsector of the photon field that violates the vacuum form of the Gauss law, then you would have to add, for instance, electrons or positrons to compensate for that. Okay. Now, basically, yeah, we want to start filling in what are the missing pieces here. And this is where quantum reference frames will come into the game. So first of all, again, somewhat conceptual level, then it will become a bit more technical. So this is according to this perspective neutral framework that I will describe. So we're going to do this now for gauge theories first. So this applies to the gauge theory side for the moment. So we have gauge, so there's redundancy. And again, as I mentioned before, you can think of a heuristically of the quantum reference frame as really a choice of a frame as being a split between what you declare the redundant degrees of freedom, which you identify with the quantum reference frame, and the physical data, which is the rest. So basically, the quantum reference frame should be, in some sense, just have the right size to absorb all the redundancy. Okay, and so then you want to use that frame, the degrees of freedom, somehow to deparameterize the gauge orbits, and in the end, you want to use it really as a proper reference frame to describe the other degrees of freedom relative to it in a non-invariant, in an invariant fashion. And so now let's become a little bit more precise. The quantum reference frame, we're going to label it by R. So R you can think of as reference or redundant. And the reference frame will come with a Hilbert space that we label HR. And it has to have a non-trivial representation of the group that we're interested in, the gauge group. And it can be a projective one. So it may not be just the unitary, it could be projective representation. It's not so important, that distinction, but I'm just mentioning that. So in order to absorb the redundancy, it has to come with a non-trivial representation, because otherwise it would be gauge invariant and you wouldn't be able to absorb any redundancy. And now this statement that the frame basically implies a split between redundant and non-redundant, basically what we mean by that is that the choice of quantum reference frame implies a choice of tensor product structure on the kinematical Hilbert space, so the total Hilbert space, so that you can factorize it into frame parts, and the rest, and we're going to call the rest simply S for a system. And that's going to be those are going to be the degrees of freedom we want to describe relative to the frame. And for simplicity, we're going to assume that the total representation of the gauge group on this total space here, that it's given by a tensor product representation, a unitary one. It's not strictly necessary, but it turns out to be sufficient for all the stabilizer codes. And if you don't make that assumption, your life gets significantly more complicated. And now let's talk a little bit more about the reference frame. So we usually think of a reference frame as having some kind of orientations. So for instance, you can think of a tetrad in special relativity, or a set of spatial vectors like rods that point in different directions, and then you change the directions in which they point, so you change the orientation. So we want to generalize that to quantum reference frames. So we will take the system to basically be it is going to be a reference frame for whatever the gauge group is that we have. So it's not necessarily a spatial temporal reference frame. It's just a reference frame for the group G that we have. Okay, so we want to use it. So it's going to be some quantum system that has configuration degrees of freedom that transform non-trivially under that gauge group, just like if you have
So can I kind of think of quantum reference frame as some kind of basically a tensor factorization of Hilbert space, which is induced by some symmetry group G. Basically it's unitary representation U of G, and you are using it to basically separate the Hilbert space in two parts and calling one of them, HR, and the other part, I don't know, you had some other notation for this, and so it's just a factorization of Hilbert space introduced by induced by some symmetry group.
Well, the symmetry group by itself doesn't give you such a factorization. But basically, so there's a little bit more involved. So yeah, we're given some H kin, so total Hilbert space. There's a unitary representation on it. And what we want to do is we want to take that space and we want to find a factorization of it, a tensor product structure factorization, such that we can split it into HR and HS in such a way that the HR tensor factor basically has just the right size to absorb all the redundancy. And what that means will hopefully become clearer in the coming slides, but that's basically the idea. In general, there will exist many different ways of doing that, I should say, and that will also become relevant in the code stuff later on. So for instance, later on, we're going to take the physical space of, say, a stabilizer code as the kinematical space, and then we're going to try and find a factorization of it, where we kind of extract a reference frame that basically absorbs the redundancy of the stabilizer group and a system that will encode all the logical data.
So basically, you're saying that the H kin has been given to you, and using the symmetry group, you factorize H kin as HR tensor HS, where all the basically the gauge degree of freedom, redundancies, they are there in the HR.
Yeah, that's basically the idea. So yeah, you're given the H kin, that's right. You're given H kin and you're given the unitary representation of G on H kin. And then, so it's like in the Pauli stabilizer code, you give me what H physical is, and you give me the stabilizer group, the representation on it. That's all we need.
Okay. And then at the same time, when we think about, let's say, quantum error correction from a stabilizer framework, it's basically decomposition of the Hilbert space as like a direct sum of, like two spaces. So you have H code space, direct sum with, like the orthogonal one. And basically you are saying that, like you are creating a mapping between these two different decomposition of Hilbert spaces.
Yeah. So actually, yeah.
That's what it is, right?
Yeah. So at first, okay. So yeah. So this will become actually important later. It turns out that so there exist many such factorizations that I mentioned on the previous slide, I guess here. There will exist, in general, there will exist many such factorizations. But we will find very special factorizations later on, where it is such that HS is really H code, basically, and HR you can think of as the, it's the redundant part. So what it will tell you is that you can write the total physical space or kinematical space as in two different ways using H code, either as a direct sum or as a direct product.
Okay.
But that is kind of non-trivial, writing it as a direct product involving H code. But I hope I will get to it because it takes a bit of time to get there. But that's kind of a part of where we're gonna go. But for the moment, we're not really on the code side here. Let's maybe focus just on quantum reference frames for the moment. And then, but maybe then you know already roughly where we want to go. So anyway, so we want to define the orientations of the frame, and so there are its configurations really. So we want to define some orientation basis of the frame, and as we want the configurations to transform non-trivially under the G transformations. A good way of doing this is by just defining a coherent state system. Okay, so we have somehow coherent states that I will just label by the group element G, and then I have a unitary representation of the gauge group G on that frame that acts on it in a G covariant way, meaning it acts like this. So I act with the group element on these basis states, and it just translates the argument of the states and up to a phase. So the phase is just it's not going to be very important, this phase. And so then basically the gauge group runs through these configurations. So what this means is that we really label the group, the frame orientations by the group elements. And why? And so at first that might seem, why would you do that? But it's really when you have a kind of perfect or a complete reference frame, then that's really what happens. So for instance, when you have a tetrad in the Lorentz group, for the Lorentz group, it takes value in the Lorentz group. Or if you take, when you think of, for instance, orthogonal bases in three-dimensional space, the orientations of those are labeled by the rotation group. And similarly, when you want to take a particle position as a frame for the translation group, the particle position takes value in the real numbers, so it takes value in the translation group. Okay, so it's just to emphasize that it's not something surprising that we're going to label frame orientations by the group itself. And when we can do this, when the states are really different, so they're not so meaning we don't have any two states G and G prime that are up to phase equal, then we can think of this really as a complete reference frame that runs through the whole group. And we're going to be focusing on what are called ideal quantum reference frames, and they are those when these orientation states are actually orthonormal. So in general, they will not be orthonormal. When you have a coherent state system, then you have some kind of overcomplete basis. But it turns out that for stabilizer codes, it's sufficient to look at these when they are actually a basis. Okay, and then these orientation observables, I can build POVMs from them. So covariant positive operator value measures by basically just looking at these kinds of things. And then those are observables for the orientation. Okay, and so what we want to do is now using these quantum reference frames, we want to fill in the missing pieces here. And so first of all, so we're going to make this assumption here that the kinematical space now factorizes in this way. Now this gauge invariant space it now has the name that it's perspective neutral. I will hopefully have the time to explain better why it's called perspective neutral. In the end, it will turn out to be a Hilbert space that will encode all the different quantum reference frame perspectives at once. So in that sense, neutral. So when we have the quantum reference frame, as I mentioned, we want to describe the rest relative to the frame. So we can think of that as describing it relative to the perspective of that reference frame. That's why we talk about perspectives here. And then the missing piece here is a redundancy-free description will be given by a Hilbert space that describes the the remaining degrees of freedom, so the system relative to the frame. So that's why relative to R. This will be a redundancy-free description. And I will now, in the coming slides, try to explain you a bit more how to think of this kind of thing. So this then fills up the Hilbert space dictionary. And now let's talk a little bit about the maps between the two to make this somewhat more precise. So in quantum error correction, you would have then from the logical space to the code space, you have these encoding maps and conversely the decoding maps. So you have your logical space and then some whatever logical state, say, and then in order to embed it in with redundancy, you add some kind of tensor factor. Here I call it ancilla. I think in the quantum error correction literature, you don't always call it ancilla, but whatever. So just some additional degrees of freedom and that are going to be in some fixed state. And then I do some non-local unitary n on the whole thing so that I spread basically the logical information in some sense as non-local a way as possible across all the degrees of freedom so that they get more or less protected from local errors. So this n is going to be usually highly entangling. Now, on the quantum reference frame side, what the analog will be basically jumping into a quantum reference frame perspective. So those will be, or the inverse of that really. So I'm just going to try and explain that. So it really will have the same kind of structure here. These are going to be maps between really this perspective neutral space and these perspectival Hilbert spaces. And let me try to explain that on a separate slide. So it's what we sometimes call jumping into quantum reference frame perspective. And I should say for the remainder now, I'm going to restrict to finite abelian groups, and that I will do because a stabilizer group is just a finite abelian group. And I will restrict to ideal quantum reference frames, so with orthonormal orientation basis, and that's just because that will suffice for the stabilizer codes later. And I do this for the explicitness of the formula here. So I can write the same formula down for more general groups, but then I have to basically replace sums by integrals and so on and so on. And so there exist two different ways of jumping into frame perspective that are unitarily equivalent. I'm just going to describe one that's most closely to this encoding. And this is something that we sometimes call an entangling or disentangling the quantum reference frame. So this is from this gauge invariant Hilbert space. So it's a map from the gauge invariant Hilbert space into whatever we call the frame perspective on the rest and the fixed frame state. This map is defined by this object here. Turns out to be a very highly non-local unitary. So an analogy to this unitary n on the quantum error correction side, the encoding map, this is also a highly non-local unitary. And what does it do? So if I take an arbitrary gauge invariant state, so you can think of that as a code state and the analog of a code state, and I act on it, then it spits out the quantum reference frame in a fixed state. The fixed state is just given by a coherent average over the group basis and times something for the rest, so for the system. And the rest here is given actually by something that is gauge fixed. So it turns out that the state here is you take the gauge invariant state and you condition on the frame being an orientation group element E. Remember that the orientations are group labeled. And here in this case, I just pick the group element, the identity, and I just gauge fix the orientation to be in the identity configuration. So when I condition on it, that's really gauge fixing, and it's a gauge fixing because these group states, they run through they transform non-trivially on the gauge transformations. They run once through the orbit. When I fix it, I fix one point on the gauge orbit. And you can think of this here really being the description of the remaining degrees of freedom relative to the reference frame when it is in a certain orientation. Given that I've frozen the reference frame to be a fixed configuration, you can think of this as being basically this gauge fixing as aligning the internal quantum reference frame with some external reference frame, okay? And okay, there exists some unitarily equivalent way that goes by pure gauge fixing, that goes by something that is known as Page-Wooders construction. Maybe you have heard of this, but here, for interest of time, I'm not going to describe this. But this is something that we had constructed in the quantum reference frame literature before, but now you see that really, when I then take the map, so from the, okay, this would be the inverse map, it really takes the exact same form as structurally as what happens within encoding. And so you can think of this quantum reference frame as being really the analog of what I call the ancilla here. And okay, for encoded logical operators, okay, I mean, you do the obvious thing on the quantum error correction sides. You take your logical operator, you also append whatever the redundant piece, and then you do the same thing. On the quantum reference frame side or the gauge theory side, really, you would do the same kind of thing, just that you take some operator that acts on the system. The interesting thing here is that this takes the form of a relational observable. And a relational observable, they are interesting in the quantum reference frame literature. So I said we want to look at this thing here. So, you know, we look at some system observable, then we have the frame and this kind of fixed thing, and then we do these disentangling maps, the analog of the encoding maps. And then with a bit of gymnastics, you can rewrite it in the following form here. And what is this pi pn? The pi pn is just a projector onto the gauge invariant Hilbert space, which is what would be the projector onto the code space in the quantum error correction literature. And you can just write it here as a coherent group averaging over the gauge transformations, okay? So this projects you onto the gauge invariant Hilbert space. And that is interesting because you can now think of this piece in the middle here. This measures this system observable Fs, given that the frame is in configuration or in the orientation G equals E, and then you project it onto the gauge invariant part. So it's a gauge invariant way of measuring Fs, given that the frame is in the orientation G equals E. So in that sense, it's a relational observable. Okay. And you can therefore think of really the analog of the logical data on the quantum reference frame side is really the relational description of the system relative to the quantum reference frame. And now on the quantum reference frame side, on the quantum error correction side, of course, we have these errors that take you from the code space to some target space. And on the quantum reference frame side, or the gauge theory side, really more generally, we can think of them as charge excitations. I think I have that on a separate slide. Yeah. So maybe let me just briefly explain that here in the for like NK Pauli stabilizer codes. I assume you know what these are. So N physical qubits, K logical qubits. And so the stabilizer group is always a product of factors of Z2. So when it's an NK stabilizer code, then it's N minus K copies of it. So that's clearly a finite abelian group. And we can take the total space as the kinematical space or the physical space. We can decompose it into irraps of this stabilizer group. And the trivial irrap is just chi equals 1. So that would correspond to the code space. And then if we look at Pauli operators that don't commute with the stabilizer group, they act as errors that take us to these irraps, the non-trivial ones. And well, for the bit flip codes, for the 3-qubit repetition code, for instance, the bit flip errors, I suppose you're probably familiar with this, given by this stabilizer group here. So this is just Z2 times Z2. And I can look at the individual bit flip errors. The encoded states look like this. So this defines you also this encoding map. The logical 0 gets mapped to a triple of zeros in the physical space, and a logical 1 to a triple of ones in the physical space. And and then I can and then these guys, they just flip these individual physical qubits and thereby create errors in your code. And now, when we want to translate that into gauge theories, we have to think a little bit conceptually for a moment what that might mean, because usually in gauge theories, the statement is that, well, we only really care about gauge invariant stuff. So we usually don't consider maps that take us out of a gauge invariant Hilbert space as being physical. So what could errors actually mean on the gauge theory side? And it turns out that there are actually ways in which you can think of them as being meaningful. So one is when you think about a quantum simulation of a gauge theory. So it means you have a quantum system that's not actually a gauge theory, but you want to restrict it to a subset of states that mimics, say, the gauge invariant Hilbert space of some lattice gauge theory. Then literally errors in the simulation, they would correspond to something that takes you out of this simulated gauge invariant Hilbert space. So they could correspond to that. But also you could have things like in surface codes or the toric codes where the gauge symmetry is really not fundamental in some sense. And so it's some kind of emergent gauge symmetry. So you can break it, which is in some sense fine because you're not really breaking a fundamental gauge symmetry. Or you can think of something else where the errors basically don't literally break gauge invariance, but they sort of unfreeze some other particle species. I think I have a better explanation of that on the next slides. So it's basically when you go from the gauge invariant Hilbert space for the pure photon field in Maxwell's theory, and then you go to it having a non-trivial charge, then it basically means you have to compensate it with like electrons or positrons. So you go from the matter vacuum sector to a non-vacuum sector, but you are not breaking actually the gauge invariance, but you basically break the original form of the Gauss law, and you go to a different form of the Gauss law. Okay, so this you can actually also model as errors. And then it also turns out, for instance, that gauge fixings, there are also other maps in gauge theories that take you, of course, out of a gauge invariant description into a description that's not manifestly gauge invariant, but it doesn't lose any gauge invariant information by definition. So it doesn't fundamentally corrupt your data. So and it turns out that they also correspond to actually correctable errors in the language of quantum error correction. And then the last piece, maybe for the interest of time, maybe let me just not mention it. Yeah, so basically here, coming back to this thing of unfreezing other degrees of freedom, this you can think of a stabilizer code as a Z2 gauge theory, and these individual bit flip errors, I can think of them in some sense as electric charge excitations that take me from the Gauss law, basically, morally speaking, the discrete version of it, I should say, delta E equals 0 to delta E equals some non-trivial rho. And this non-trivial rho, this will label then the non-trivial irreps in this decomposition. So that's why you can think of these maps as errors or as electric charge excitations when you interpret this like a abelian gauge theory. Okay, so this is just to say that it does actually make sense to think of errors in gauge theories. There is a physically meaningful way, or there are meaningful ways of thinking about them in those contexts also. Okay, and in the interest of time, let me maybe be a bit quick on the coming things so that I can come to some applications of this dictionary. So of course, on the quantum error correction side, one is also interested in error channels that somehow model specific implementation of an error model that take code words to some corrupted states. I mean, I guess you're all quite familiar with it. And obviously one is interested in sort of recovery operations that basically correct the errors that have happened, including some syndrome measurement maybe. And so you recover the original code word from the corrupted data by some recovery operation. And so on the gauge theory side or quantum reference frame sides, when you think about what I said before, that it does make sense to think of errors as, for instance, charge excitations. You could think about the same kind of channels and think about them as sort of charge excitation channels and the recovery operations as de-excitation operations and so on. So you can think of this in similar ways. I'm just going to mention that here because it's somewhat interesting, but I'm not going to go into the details here for the interest of time. And then maybe one last thing that also comes towards explaining why this approach to quantum reference frames is called perspective neutral. So as I mentioned, there's many different splits that you can have into redundant and non-redundant in gauge series. And so you can have many different choices of quantum reference frame in a given gauge theory. And this has in recent years led to this new field of quantum reference frame covariance. So you look at what happens when you want to change quantum reference frame in your problem and how do physical properties change under this. This is not going to be terribly important for what is going to follow, but I just want to briefly mention it because that was the original motivation for looking for quantum reference frames, because they're used, for instance, in gauge theories and gravity to think about sort of quantum extensions of covariance principles in quantum gravity. So that's not so important here in this talk, but I just wanted to mention this so that you are aware of it. And so, for instance, what I forgot to mention before is that, so basically I told you we have this gauge invariant Hilbert space, and then we can do these jumping into quantum reference frame perspective. Actually, here I'm giving you the version that I didn't explain. I'm sorry, I forgot this, but this is equivalent to the one that I described before. So don't worry about the details here. So it's really just this kind of map that takes us from the gauge invariant space into the perspective of a frame. It turns out that it's an invertible map, and I can define this for a second quantum reference frame. And because it's an invertible map, so I can take it into one frame perspective or into another frame perspective. But because it's invertible, I can build something like quantum coordinate transformations, really that look like coordinate transformations on a manifold. I can invert this map. So when I'm here, I can invert this map. I go back to this gauge invariant Hilbert space, and I can concatenate it with a forward map into the new Hilbert frame perspective. And so this operation is like this. This defines a map from here to there, like a quantum coordinate transformation, and that's a quantum reference frame transformation. Okay, and so in this here, Hilbert space thereby really encodes all the different quantum reference frame perspectives. It really links all these quantum reference frame perspectives, just like a manifold links all the different coordinate descriptions, say in relativity or so. So like the manifold itself is like a linking frame neutral or coordinate neutral object. This gauge invariant Hilbert space links all the internal quantum reference frame perspectives and is thereby sort of internal quantum reference frame perspective neutral. So that's the origin of the name, why this has the, PN as a label, why it's a perspective neutral Hilbert space, and why the whole framework is called perspective neutral. So that really has something to do with the reference frame covariance that I'm not going to discuss further, but I just wanted to explain what the origin is. And on the
sorry, Philip. So
yeah.
Just a quick clarification. So like this non-unique thing, like from your last slide. So I mean, like here, like we just could I think of this as like just mapping like this R subsystem to like just to different bases? Because like here, like you have like G and G prime. So does that like correspond to like just different measurement outcome when I think of this as
okay, sorry, let me I have to figure out how to write here in this sorry. So yeah, basically so suppose we're given some factorization into HR tensor HS, right? So that's for one frame, but now the statement is we can also factorize it in some different way, R prime tensor HS prime.
Yeah.
And the R prime will overlap with, in general, both of these here. And so it will be non-local in the original. So it's really the two tensor products that I'm drawing there are distinct in general. And really, the gauge invariant Hilbert space, this perspective neutral space is independent of this factorization, really. But really, when I do these decoding maps or these jumping to frame perspective, they depend, of course, on the choice of frame that I've made. So before I gave you a different definition than the one that I'm giving you here, but basically this one here is the Page Wooders one that I'm giving. You're really just conditioning on the frame orientation. It's really a gauge fixing. It's only a gauge fixing here. And so you might at first wonder, why is that an invertible map? So it turns out, of course, that when I apply this map here, because I'm conditioning on something, it's not an invertible map on this full Hilbert space. It turns out to be an invertible map on the subspace HPN. And that has to do with the redundancy. All I'm doing is I'm gauge fixing. And by gauge fixing, I'm not throwing away any gauge invariant information. And that's why it turns out to be invertible. So that's kind of the heuristic way of thinking about it. And so really here in this way, jumping into the different frame perspective is really just two different ways of gauge fixing, okay? And so, and the quantum reference frame transformations between the two is implemented by a type of quantum, of gauge transformation. Really, you can think of that as a gauge transformation. Nevertheless, it turns out that the choice of quantum reference frame itself is not a gauge choice. That's why actually the quantum reference frame changes, they're not just pure gauge, okay? So it is actually something physical. It's something that you can describe purely in terms of gauge invariant information. But yeah, at the end of the day, it will amount to you're really just taking different reference structures relative to which you describe other degrees of freedom. And so at the level of the gauge invariant algebras, this will basically correspond to different factorizations of your gauge invariant algebra. So it's it is something that is purely gauge invariant, but it's really the main message is you have different relational ways. So all of these descriptions are going to be relational. You describe a system relative to frame in an invariant fashion. And when you choose a different reference frame, you have a different system, but you can still describe it in a gauge invariant way. And these observables, when I look at the full set of observables, it generates the full gauge invariant algebra, but it gives, in some sense, a different description of that gauge invariant algebra.
So, would that be equivalent to like kind of like changing your code from one code to another? Is that kind of like what?
No. So it doesn't, because I'm not changing HPN. So HPN is fixed. HPN is the analog of H code.
Yeah.
But okay, maybe I should just go to the next slides because I think that will hopefully answer your question. Because you can think of these maps really as decoding maps, because they take me, this is like the logical spaces, right? So these are like, these guys here are like the decoding maps. So you can think of a quantum reference frame transformation as a change of encoding or a change of decoding, but it's the same code space. Okay. So this is basically what I wanted to say here on the next, here. That's basically what I wanted to say. So you can think of this as having like a second H logical here, prime or so, and then you encode it in different ways, yeah.
Okay, I see.
Yeah.
But you're still encoding to the same subspace?
Yeah. So you're still encoding to the same, so you don't change H physical, you don't change H code, but you basically decode to a different logical space.
Okay.
So this is something that you don't usually consider in quantum error correction. I think usually you fix your logical space, but of course it's clear that once I encode it into a given, once I go this way, I mean it's clear I can find it decoding to a different space. I mean that's I can. I mean, that should be fairly clear, right? So it has to do with the redundancy again. The code space encodes, of course, also for redundancy, but redundancy is never, which degrees of freedom are redundant is not told to you by the system. There's a freedom of choice. And so, so basically this part here, I mean, this thing here is not usually considered in quantum error correction, but you could consider it. You can change your encoding, and that would amount to what is a quantum reference frame transformation on the gauge theory side.
Interesting.
Yeah. So I mean, I'm not going to talk further about this last thing. I just wanted to mention it because these quantum reference frame transformations, they have received a bit of attention in recent years, and it kind of has generated a new subfield that interfaces quantum foundations, quantum gravity, and so on. And there is an analog on the quantum error correction side, which is this change of encoding. But yeah, people, I guess, don't usually look at it, and on that side at least. Okay, maybe let me go on because it seems like I have like 5 minutes or so. Yeah. So, or how much time do I have roughly left? Is it 5 minutes? Because then I'm gonna skip this one here probably.
I think about like 10 minutes or so should be fine because we started a bit later. Yeah.
Okay. But okay, maybe I'm just gonna do this one here a little bit quicker. This is the next topic I'm gonna talk about is the most interesting one. So far I've just basically told you, summarize the dictionary. Kind of had to tell you about these different structures so that you know. So this is basically the precise dictionary that you can write down about. It's a summary of it. So that tells you really there's an exact correspondence between at least group-based codes and gauge theories. And at least when you for a fixed group G. And so here now we want to go a little bit and see what we can learn from this. And so the first slide here is about extracting quantum reference frames and stabilizer codes, and the first way using the original. Oops, I guess I didn't want the. Okay, whatever. Is using the physical space, the tensor factorization, the original one that you start out with. So. And the statements you can always find. So we start from the quantum error correction side. So you give me some physical space like this. So some NK stabilizer code with some stabilizer group like this. And the statement is you can always find ideal quantum reference frames inside that code, which are built from physical qubits. Okay, what I mean by that is you find a partition of the physical qubits that sit inside, such that you can pick n. There always exists a choice of n minus k of these physical qubits that define a frame Hilbert space HR, and the remaining k physical qubits define the system in such a way that on this HR, so on these n minus k physical qubits, I can find a covariant orthonormal frame orientation basis that satisfies these properties that I used in the definition of quantum reference frames before, that is actually orthonormal. In general, there will be some non-trivial phase here, but it's not so important. So it's just to say that, okay, there actually exists a sort of fairly simple way in which you can get this. So and just to illustrate this, in the repetition code, the 3-qubit repetition code, when you have the stabilizer group like this, which is Z2 times Z2, so the code states are given, or the basis is given by this here. You can you can choose the first 2 qubits here. Let's call them 1 and 2. You can define as your frame. It turns out in a representation of the stabilizer group here on that frame is basically just given always by the first 2 tensor factors of these 4 elements. Okay, the first one is then just the identity. The second one is just so this would be this one here. This would correspond to Z on the first. No, sorry, that would be this one here. Sorry. Anyway, so the precise details here, maybe in the interest of time, not so important, but it's basically you pick the first 2 tensor factors of each of these 4 group elements, and they will look like this here. And it turns out that it gives you a faithful representation of the stabilizer group on the first 2 qubits. And then you can just pick the X basis, and you define that as being your group basis, the orientation basis. It's evidently orthonormal. And when you act with these guys on it, it will just run through the group labels. It's something you can easily convince yourself just because the Z's here, they flip the X's, okay? So this here will define you something like that. And now, and then you would define the system to be the 3rd qubit. And then basically the 3rd qubit, the representation of the group is just basically always the 3rd tensor factor from these 4 elements. And that gives you something like this. And then you have a consistent description. By multiplying the representation here with this, you always get back the corresponding element here. So this is a kind of simple way in a very simple code how you can do this. One thing here is that the system has a non-trivial representation still of the stabilizer group, so it's not already invariant. It's not purely logical. Okay, so in general, this factorization here is giving you a definition of a quantum reference frame inside a stabilizer code, which is well, it has an ideal frame, but the system is not yet completely invariant. It's not completely logical yet. So you could build all these relational observables and do some of the stuff I said before to extract the logical information from it. But it turns out that there's an even more elegant way of doing it, and that will define an exact correspondence between correctable error sets and choices of quantum reference frames, specific choice of quantum reference frames that actually shed some light on what it means for error sets to be correctable and give you a reinterpretation of the Knill-Lam condition. So I hope I can still run through this because that's kind of, in some sense, technically a main result from our paper. So yeah, I guess, as I said in the beginning, error correction relies on the existence of redundancy. And quantum reference frames formalize the redundancy. They absorb the redundancy. So we can ask now whether we can understand the connection between correctability of error sets and redundancy in a very precise way using quantum reference frames. And the answer is yes. And in order to do so, I need a bit of structure. So I guess I don't really need to explain that to you guys if you're a quantum error correction focus group. Yeah, I mean, you have some set of errors labeled by I is correctable if and only if the Knill-Lam condition is satisfied, meaning this here is satisfied, where pi code is just a projector onto the code subspace. And then when you look at this combination here, it must be proportional to pi code, where Cij is just some Hermitian coefficient matrix. And essentially, this relation means that you can always find a basis of errors inside the span of this, such that the errors map to mutually orthogonal error spaces that you can perfectly distinguish. So you can distinguish the errors, and these error spaces are also of the same dimension as the code space. And in this way, you basically lose no information, and you can find ways of detecting the error and inverting the errors. So in a nutshell, but I guess I don't really need to explain that to you guys. So that is just what it means for errors to be correctable. Now, what is also clear is that when we look at errors, really what matters is the code space restriction. So EI times pi code. And that's what matters for this here. But more generally, I guess we only care about what errors do to code words, not what they do to corrupted code words. And so we're going to focus on this. And we want to somehow focus really just on correctable error sets. And we don't care now about the precise basis for an error set. We will only care about the span, really, okay? So, and I will, because at the end of the day, it doesn't matter what basis we choose. And so we're going to consider two error sets to be E and E prime to be equivalent if the linear span of the code space restriction is the same. So that's just, so we were going to be considering equivalence classes of error sets if their spans are going to be the same. The code space restriction of the span is the same. And then one more thing is we want to look at maximal sets of correctable errors. So maximality notion is important in order to define quantum reference frames. And maximality will mean that an error set is maximal if this coefficient matrix Cij is basically of maximal rank among all the possible ranks it could have among all the possible error sets. And in NK stabilizer codes, this just means that it's of rank 2 to the n minus k. Okay, so this is just as a few ingredients. So now I come to the main, essentially the main theorem of the paper that establishes really a two-way correspondence between correctable error sets or equivalence classes of correctable error sets in quantum reference frames. And so the statement is, so you give me any NK stabilizer code, so that's a given. And now let's start with one direction of this theorem. The statement is now any maximal correctable set of Pauli errors labeled by this, so it includes the identity, so it's part of the Pauli group, generates a unique ideal quantum reference frame such that the code's restricted errors and the stabilizer transformations act trivially on the system. So what I mean by that is that any such maximal set of correctable errors defines a reference frame R. So such a basically a factorization of the physical space into a frame tensor HS I should emphasize that this tensor product in general is not going to be the same as the original one of the physical space we started out with. It's in general going to be a very non-local one in terms of the original one. And the statement is that the frame is such that when I look at the code space restriction of the errors in this new factorization, they act only on the frame part and trivially on the system for all of these errors. And when I look at the representation of the stabilizer group in this new factorization, it acts trivially on the system, but non-trivially on the frame. So the statement is that always exists for any maximal set of correctable Pauli errors. And what do I mean by generates here? What I mean by that is that if I look at the star algebra, so star algebra means it's an algebra that's not only closed under linear addition and multiplication, but also under conjugation, so under dagger relations. So if I look at the star algebra generated by these code space restricted errors, so these guys, so I look at the algebra generated by them, then you can prove that it is equivalent, or it's isomorphic to the set of operators on an n minus k qubit Hilbert space. This Hilbert space we're going to identify with this HR here. And it turns out that this algebra only depends on the equivalence class of this error set. So you pick any maximal set of correctable errors that has the same span as the original set. It will define the same reference frame. That's the same statement. The other statement is that the stabilizer group is contained in this algebra. This is the origin of why it will only act on the frame part, because it's contained in the frame algebra. And what we're going to do is we're going to define the system as being the commutant of the frame algebra. So it's going to be the algebra given by all the operators on the physical space that commute with this algebra. Okay, and then it turns out these are factors, and they actually together generate all the operators on the original space, and thereby they actually define. They give you an algebraic way of defining a tensor product, and that tensor product is then this one here. Okay, and this means in particular that if I take the system to be the commutant of the reference frame, and the reference frame contains the stabilizer group, then it means by definition then the system commutes with a stabilizer group, so it's gauge invariant. So this also explains this form. Or gauge invariant, it's purely logical. So it means the frame really now absorbs all the redundancy. And so the statement is this exists for any maximal set of correctable errors, and it only depends on the equivalence class of this maximal set. But in general, there are going to be many different equivalence classes. So there will exist many different such factorizations of the physical space that have this property. And there's also a converse. So here the statement is basically you give me an equivalence class of maximal sets of correctable errors. To that, there corresponds a unique quantum reference frame with these special properties. And now the converse is also true. You give me a quantum reference frame with these special properties, and there corresponds to it a unique equivalence class of maximal sets of correctable errors whose code space restriction only acts on the frame. So it's really a correspondence that goes in two ways. And so this theorem, why is that actually interesting? So it really has something that has you can take that to reinterpret the Kniller-Flamm condition. And the statement now is, as a corollary of that theorem, we have that a set of Pauli operators, Pauli errors, and it doesn't have to be maximal set anymore. It can be any set of Pauli errors. It is correctable if and only if there exists a quantum reference frame R such that the stabilizer group UG and the code space restriction of these errors acts exclusively on the reference frame and trivially on its complement, the system S. So one direction of this corollary is implied by the theorem, because any error set I can upgrade to a maximal one. And the theorem tells us when I have a maximal such error set, then it generates a quantum reference frame that has these properties. Now, the converse direction requires sort of 3 lines of proof, but it's also pretty clear that if you have a quantum reference frame that has these properties, and then the errors act only on it, that's, well, they're going to be correctable, that's essentially because in that case, there are no logical errors, okay, that act only on the frame. And so this allows you to really make the link between redundancy and correctability of errors fully transparent. So yeah, errors are really correctable if and only if you can find such a split between redundant information and non-redundant information, and such that the errors and the stabilizer group act purely on the redundant piece. So that makes it then very unsurprising that such errors are correctable and don't fundamentally corrupt your logical data, because the logical data is really basically encoded in the system and it's completely unaffected by the stabilizer group and the errors. Okay, and so in the statements you can find this kind of factorization for any set of errors, any maximal set of errors. Okay, so this is so this kind of tells you a little bit. You can see that how this picture with quantum reference frames, at least to us, it seems like this is something new on the quantum error correction side. We were not aware that such an observation exists in the quantum error correction literature, but since we're not total experts on the literature, we cannot be 100% sure that something similar exists on the quantum error correction side. In the literature, sorry, I should say. If you know something, then please let us know. But we did talk to a couple of quantum error correction experts, and some of this kind of relation here wasn't known to them. So anyway, I'm going to skip the error duality part since we're over time. Just in a nutshell, it's basically using quantum reference frames. You can define a new class of errors that you can interpret as gauge fixing errors. They're not errors in gauge fixing, but they implement a gauge fixing, and the gauge fixing itself acts like an error that takes us out of the gauge invariant Hilbert space, so it takes us out of the code space. And these gauge fixing errors satisfy Knill-Laflamme and blah blah blah, and so there exists recovery operations and blah blah blah. And it turns out, okay, there's a certain Pontryagin duality that I'm now not going to explain. But you can think of that really as a discrete version of position momentum duality. And these errors that you get in this way, they are kind of dual to the standard Pauli errors that we consider in stabilizer codes, where you can think of the standard errors in stabilizer codes like they're in some sense like electric charge excitations that I mentioned, and these kind of gauge fixing errors, you can think of them as magnetic errors. So Pontryagin duality also gives you a form of electromagnetic duality, I should say. And okay, you get basically for this new class of errors the same kind of structures as you did for the standard Pauli errors. And there's a certain duality mapping between them. So, okay, we found that quite interesting, but in the interest of time, I'm not going to discuss this. So there's some information on that in the paper. But yeah, so here's the conclusion. So really, what did we do? So we have really an exact correspondence between group-based quantum error correcting codes and quantum reference frames. So really an exact dictionary, really between group-based codes and this perspective neutral framework of quantum reference frames. So if you're interested in quantum error correction, you should be interested in quantum reference frames. And if you're interested in quantum reference frames, you should be interested in quantum error correction. And for any stabilizer codes, we can find local ideal quantum reference frames, as I mentioned. And then really a kind of nice result is this error sets, correctable error sets, quantum reference frame correspondence, that for every maximal set of quantum error of maximal sets of correctable errors, there is a unique quantum reference frame associated with it in stabilizer codes. And then we have this reinterpretation of the Knill-Laflamme condition that really makes it crystal clear the connection between correctability and redundancy. And okay, that's this error duality that I didn't really explain. And okay, now we can ask, what can we do with this? So all of what we've done so far is really, at this moment, I mean, it's the first paper on this correspondence, really just a more foundational work to start building this up. A question one can ask, obviously, is this going to be useful for anything in practice? So might it be useful for quantum simulations of gauge theories, for instance? That's actually a big topic. Can it help to build more efficient codes for simulating gauge theories by basically aligning the codes of the simulation with the gauge invariant Hilbert space, or like the code space of the gauge theories? can we use this correspondence in useful ways for defining or designing new codes? Because, for instance, on the group series side, we have much more control. On the quantum reference frame side, there's really a well-developed tool set that we can use. On the quantum error correction side, looking at, for instance, stabilizer groups that are non-abelian or such kinds of things, it's not so well developed. One could try and explore that more with this correspondence. And then more generally, also kind of give us sort of new insights, foundational insights into quantum error correction and gauge theories, like this error sets, quantum reference frame correspondence, and this reinterpretation of Knoeller-Flamm, or also in gauge theories. Can we learn something new about, for instance, can we think about the distribution of gauge invariant quantum information space-time as really being defining a quantum code or something like this? And so these are kinds of things that we're further exploring. So yeah, sorry for going a bit over time, and yeah, thanks a lot for your attention.
Awesome. Yeah, thanks, Philip, for the very nice talk. So yeah, let's just open the floor for any question. You can just unmute yourself and ask away. Okay, I mean, like, so in the meantime, I'll just ask a question again. So I'm still kind of like thinking about like that switching between like encoding and decoding map, and I'm I'm just thinking because, like, I mean, as you mentioned, like, people don't really think much about that in error correction, like, how you can. So basically, like, what happened there is that you keep your logical subspace fixed, but then, like, you can somehow change your encoding and decoding map where there are like there the original logical space will be kind of different, but I imagine like the H logical, or like, I don't know, H logical and H logical prime would be isomorphic, right?
Yeah, sure. I mean, they're of course isomorphic. Yeah. I mean, it's just like on the quantum reference frame side, when I do a quantum reference frame transformation, this is actually a unitary. But it turns out to be, what is important is it's a non-local unitary. So in that sense, it's really, so that's important because, I mean, if it was just a local unitary, you wouldn't really change much except like a local basis change. But these quantum reference frames, yeah, they're non-local unitaries. And that's also, in fact, one of the reasons why people got really interested in this quantum reference frame covariance business, because it means it changes correlations, entropies, entanglement, everything gets changed by these quantum reference frame transformations. And then thermal properties and all that kind of stuff becomes now quantum reference frame dependent in gauge systems and so on. So those were things that were not appreciated before. And so this is what got a lot of people really interested in this kind of thing. And for the quantum error correction side, it's also natural that when you change your encoding, it's really only interesting when it's a non-local unitary, right? Because then otherwise, okay, I just do a local basis change. I don't really change anything. But yeah, basically here, if I look at this thing here, right? So this is my code word now. I have defined it using this original logical space, and then whatever the complement of this is that I call it ancilla, and then in some unitary. But now I can just rewrite that as I can just take this row code and now define some other non-local unitary and prime and conjugate it with it to define that into something, to map it to something where I have some, like like some ready state, some ancilla ready state on some other degrees of freedom, plus tensor something else, where the tensor else is then your row prime logical or so. So that I can, of course, always do. I just change the unitary here that I use, right? So, I mean, there will always exist ways of doing that. And so it's just changing what the main point here is, of course, this ancilla, some of what I call an ancilla, really just, that's basically defining your redundancy, right? So it's just eating up the redundancy. I'm fixing the state of it. But and I fix the encoding by taking the by taking a fixed n, and then but yeah, once I have defined this, I can now conjugate the row code by a different non-local unitary, some different disentangling unitary that maps this to a different product of 1 tensor row logical prime, and that would be a different encoding or a different decoding. But yeah, I mean, I haven't really seen this in the error correction literature that people consider this, and that's presumably because maybe practically you don't really care about it because you have somehow in mind, okay, here's my here's somehow the register, and here's a specific code, and okay, that's this one way that I want to encode what I want to do with the computer or the message that I want to send or whatever, and so I just care about one way of embedding that information. But yeah.
Yeah. Yeah, no, I'm just thinking like probably like one could like kind of like look into that, like to see like the efficiency, like the I don't know, like circuit size of the encoding circuit or like decoding. I don't know, like if that's
you mean, yeah, right. So I guess in quantum error correction, okay, this is something that, so my background is more gauge theory, is gravity and so on. But yeah, I guess in quantum error correction, indeed, I guess more practically, I guess indeed you think about circuits to implement your map n, right? So and then you look at how efficient that is. Yeah, okay. Yeah, indeed. I mean, I guess you could. So yeah, this is not something that we worry about here on the on the gauge theory side. But yeah, I don't know. Yeah, indeed, one could ask whether different encodings or decodings are more efficient than others. I don't know if maybe somehow qualitatively, if they're all disentangling. So when I start from a fixed row code and want to write it in different ways as, a pure redundant piece with a fixed ready state, tensor or something else, whether maybe in some sense all of those decodings are equally complex in terms of circuits, but I'm not sure. I mean, okay, I guess it probably depends on what sort of basis sets of gates you have at hand, right? I mean, probably they're all, I mean, they should be, as if you're allowed to vary the gate sets, then they're probably all in some sense equally complex. But if you have one fixed gate set, then maybe, yeah, indeed, maybe then they may be more efficient than others.
Right. Yeah. I mean, like usually like people just use like this Clifford gate set and stuff like for like encodings and decoding. So yeah, I don't know. Like I'm just thinking that could probably like some connection there between like the complexity and that.
Yeah, that's interesting. I mean, yeah, so we definitely didn't think about this so far. Yeah, that's true.
Sounds good.
Yeah, that sounds like an interesting question. Yeah.
What notion of complexity do you mean? Sorry, Andrew.
I'm just thinking because like Philip mentioned that you can like change between like different encoding and decoding maps, which are sort of equivalent, but like it kind of like maps like different H logicals. And I'm just thinking like probably like if we look at those different encoding and decoding maps, like we could kind of like compare between them, like which one could be implemented with least number of Clifford gates, for instance. So
it's more like a get state complexity.
Exactly, yeah. Yeah, like
okay.
just a circuit size.
Okay. That sounds interesting.
Happily. So maybe I have a simple question. So I'm just wondering, in quantum error correction, there is an important concept called error threshold, which basically means that if your physical error rate is this and some threshold, and then you can somehow increase decrease the logical error rate by increasing the code distance. So I'm wondering if there's some corresponding concepts that can be found in quantum reference frame.
So you're kind of in broad terms asking about code distance?
No, it's so in quantum error correction, there is an important concept. So it's called error threshold.
Oh, error threshold. Okay.
Yeah.
I'm not sure off the top of my head what the corresponding can you remind me how exactly it is defined on the quantum error correction side? So my background is not quantum error correction. I mean, I'm familiar with aspects of it, but how's the error threshold defined?
Yeah. So I think like in simple language, it's like the physical error rate of your your system or your quantum error correction code. It's below some threshold. Then you can somehow if the physical error rate is below some threshold, and then you can decrease the logical error rate by increasing the code distance.
Okay.
Yeah.
Okay, yeah, I think off the top of my head, I don't think I have a good answer to that. Yeah, so I mean, there's indeed, I mean, the dictionary that we spelled out is not, I mean, it's not complete in some sense. I mean, there's of course aspects of quantum error correction we have not looked at, what that might mean on the quantum reference frame or gauge theory side, and conversely, I mean, in some sense we start at the dictionary, but so for instance, another thing that we haven't, where we don't really have a good interpretation yet is, for instance, code distance, what that means on the quantum reference frame side and gauge theory side. That's, for instance, also a question. So it's not, yeah, in some sense, the dictionary that we have spelled out so far is neither exclusive nor inclusive. So inclusive in the sense that it doesn't contain everything yet you can say about this correspondence, and it's not exclusive in the sense that the things that are not already in the dictionary cannot also be included in the dictionary in a meaningful way. But yeah, so that sounds like, yeah, another good question.
Yeah.
And off the top of my head, I don't have a good answer to it. Yeah.
I see. Thanks.
I have one small, maybe, I don't know, maybe I cannot call it a question or something, but it's more like a comment or maybe a question. So I don't know whether you discussed, but there is this notion of, subsystem code, which already has this thing called a gauge group. And within the gauge group, you have like the stabilizer group is basically, like the something that it commutes with the elements of the gauge group. And then there in the subsystem code, you have this notion of, like gauge qubits, which are which hold information which is other than logical information, and you can corrupt them or whatever, but the presence of such gauge qubits, is helpful, for quantum error correction in subsystem code. So I mean, so you try to map with the Hilbert space, which is factorized as direct sum of C and C perp. But I don't know, maybe it might be interesting to look at, connections with subsystem codes where such gauge freedoms are, if you haven't looked at, yeah.
Well, yeah, I mean, so we have a comment on, so, I mean, I guess the subsystem codes, a somewhat generalization of it is this, what is called the operator algebra quantum error correction. So that includes the subsystem code. So we have a comment on the relation to operator algebra quantum error correction in our paper. So where it's about correcting sort of algebras. So basically, yeah, it's true that we don't fully, well, with the stabilizer code business that I've described here, we're not fully capturing the full force of subsystem codes or operator algebra quantum error correction. And basically, I guess you can think of the codes we're looking at here as subsystem codes with a trivial gauge part, right? So when you talk about subsystem codes, you have that it's somehow, I don't know how to write it, but maybe comp tensor H gauge, right? But the important thing is that it's a factorization of the code space, not of the physical space. And in our case, basically, you can think of the codes that we're dealing with as cases where this here is just, C, so just one-dimensional. So, but yeah, the non-trivial subsystem codes are when these H gauge are of higher dimension. And at least, I mean, because we were just dealing with, here in the main part that I discussed with standard stabilizer codes, we haven't considered sort of non-trivial subsystem codes where this gauge part is of higher dimension. But yeah, but yeah, I guess it's important to emphasize that this H gauge here, a priori, is not to be confused with this HR that I used here, right? So, I mean, one thing is that this H physical here is really, you can think of this H gauge, HR here, and this H system, you can think of it as H code. So basically, we're looking at a factorization of the physical space in terms of the frame and the code space. And so that's interesting when you contrast it with H code, direct sum H code perp. So that there exists also a way in which you can use H code to factorize it. But yeah, I guess here with the subsystem codes, you're asking about a different structure where actually the H code itself factorizes in non-trivial ways. And that doesn't appear to be the case here in these stabilizer codes.
I see. Yeah. So basically, yeah, like, I mean, the code itself factorizes as, like a subsystem part, like, I mean, they're like the gauge and yeah.
Yeah, that's right. So this is, I mean, okay. So in unpublished work, we have cases of that, but that's not a standard stabilizer code. So
that is correct.
So yeah, this result here, this error set correspondence is really, it has a priori nothing really to do with the subsystem code structure. That's different.
All right, cool. So see if there's any more question. Yeah, so if not, yeah, let's thank Philipp again. And yeah, so
Perfect, my pleasure.
yeah, it's been very interesting because like we don't get a lot of like this kind of like talk connecting quantum foundations with error correction. So this is yeah, kind of like something a little bit different and very interesting.
Yeah, well, I mean, this is also not only about quantum foundations, but also gauge theory, so high energy physics actually.
Yeah, okay.
Yeah, because the quantum reference